Hello Caterpillar, we are Group 1, and today we'll be discussing the transportation mode optimization for cat logistics in Latin America. My name is Andrew Michelotti, and my fellow group members are Maggie Condon, Kayla Maxon, Liam Murray, Casey Walker, and Megan Williams. Today we'll begin by introducing the problem statement, followed by a recommendation, a current state analysis, an explanation and demonstration of our model, and takeaways from our transportation mode comparison model before wrapping up with our final recommendations. The problem that we are addressing today is Caterpillar dealers lacking a standardized method of selecting a transportation mode for product delivery, and thus not fully optimizing their service level or total cost for their operations in Latin America. In order to solve this problem, we recommend that Caterpillar dealers in Latin America follow a 60-day forecasting cycle to allow for an optimal number of ground shipments. If a dealer needs a part in 60 days, the transportation mode comparison model, TMCM, should be used to find the most effective transportation mode. In approaching the case, we first wanted to make sure to fully understand CAT's current state. We noticed a lack of standardized processes across CAT dealers where decisions were made on rule of thumb rather than data-driven rationale. This contradicts CAT's reputation of being a world leader in customer support, since accuracy in stocking, inventory, and transportation impact overall performance. To us, this reaffirmed the importance of developing a means to select transportation modes and provide consistency to dealer performance and services. Currently, 11,078 parts are shipped via air compared to 23,557 via ground transportation. We were curious to see how our model would change these figures and improve dealer performance. I will now pass it off to Megan to introduce you to our transportation mode comparison model.
Thank you, Andrew. After analyzing our current state of mode selection process, we worked together to come up with a standardized model to aid in the decision-making of the mode selection process. Our model is the transportation mode comparison model, or TMCM, which Andrew referenced. This model is designed to aid a dealer in deciding the optimal transportation mode with quantity changing and time needed for a part. It combines this data with the SKU data and store data that has been previously gathered. In order to best understand the model and how it can be fully utilized, we would like to give a brief overview of how the process works. This model is set up by store and part number. For each dealer, they are able to look at each part separately in order to find the best mode transportation. On the Options tab, you can see a list of the parts currently purchased for each store. If a part is added to their stock, the data can just be added to the SKU data, and the model will incorporate the information. To start, a dealer will select his or her store and the part number they are looking to order. After choosing the part number, they are able to select the quantity to order and the amount of time needed. As you may expect, as these constraints change, the carrying costs and the transportation costs associated with the model also change. These changes further affect our service level and the feasibility of each different model of transportation. What is important to understand about the model is that dealer analysis is needed to make an ultimate decision. The dashboard shows all the different possibilities and the costs based on the information inputted, but it is up to the dealer to look at the various scenarios based on the quantity and time needed, which can be seen here. As they change the quantity, the cost goes up. As they change the time needed, the feasibility of modes and service levels change. My fellow colleagues will go into further depth with the model about the transportation costs, service levels, and finally, how to weigh the benefit of cost of transportation and carrying cost. I'll now hand it off to Casey to go into depth about our transportation calculations and the impact of containers.
Thank you, Megan. One factor that is often overlooked in logistics is container optimization. In the supply chain realm, there are hundreds, if not thousands, of different containers to potentially ship materials in. When we began creating our container optimization section of the model, we first began this by simplifying the potential containers we could use. We determined that suppliers would most likely ship materials in either corrugated boxes or returnable bulk plastic containers. More specifically, we picked 4 different sizes of each type of container for Caterpillar to ship the materials to dealers. We then determined the different dimensions, weights, and weight capacities for each type of container. After we determined the potential candidate containers, we then created a formula in Excel that compares the dimensions and weight of a given part and the internal dimensions and capacity of all of the container options. We then created another formula that that selects the most applicable container based on the amount being shipped. The final output of this section of our model is the optimal container, maximum quantity of said container, and the weight of said container. This information can be used to ensure you're using a container that's not too big and also not too small, thus reducing costs by decreasing shipping weight and allowing for more containers to be shipped at a time. We use this information combined with the weight of each part and the quantity to be ordered to determine the transportation costs based on dollars per kilogram. Now that we've fully explained how costs factor into our model, Kayla will walk you through the impact of service level.
While our model is very cost-focused, we also knew that it was important to include service level since CAP prides itself on service. Service level is the probability of not having a stockout, so ideally we wanted to build a model that would calculate expected service level and allow us to select the transportation mode with the highest service level to be the optimal solution. There were two main metrics that we used in calculating service level: the marginal unit cost of stockout and the carrying cost per unit for the lead time. Using these metrics, we were able to calculate service level for each mode of transportation. With this service level calculation, our model shows that the service level is higher for transportation modes involving air as opposed to transportation modes involving surface transportation. This is somewhat surprising given the fact that there is more variability in surface transportation, meaning there's a greater risk of a shipment arriving late and causing a stockout. However, since our model places such a heavy emphasis on only the feasible solutions that meet the required lead time, service levels are better for transportation modes like air that have shorter lead times since there's usually more buffer before reaching the required lead time. We think that if communicated clearly to dealers, this aspect of our model will not cause them to indiscriminately favor air transportation due to the higher service level, but instead help them understand the lead time on their transportation mode decision and its impact on stock and carrying cost. To discuss the trade-offs between carrying cost and transportation mode, illustrated by our model even further, I will now hand it off to Manny.
Thank you, Kayla. As we saw in the SKU data, numerous parts are ordered by the dealers in very small quantities, sometimes only once over the course of the year. A dealer forecasting a situation like this could face great difficulty due to the small order quantity. That said, our model is able to help dealers know at what point the carrying costs outweigh the cost of emergency shipping the product. To illustrate, let's look at a part that was ordered only once this year. Part 3320 for store number 49. If we plug in the quantity of 1 and a lead time of 45, we can take a look at the graph and see the upward sloping yellow line. This represents the sunk cost of shipping because a part must be shipped and how the carrying cost increases each day. The horizontal lines represent the cost of simply waiting for a customer to request the part be ordered and then place the order, and then once it's delivered, the dealer simply gives the customer the part without incurring any carrying cost. Air, of course, will be the most expensive, and the graph explains that unless you know the customer will be requesting the product in less than 13 days, it would be much better to ship by air and incur the same cost or less when compared to how much would be paid for the carrying costs. This graph will, of course, change should quantity increase and the days of the carrying cost product decrease. Here are the takeaways from our transportation mode comparison model. Some of the benefits we hit on were the flexibility built into the model, as well as the easy implementation outside of just Latin America. Our limitations include some of the assumptions that we made, as well as the lack of automatic analysis. Something that is very important to remember is the need for a 60-day cycle plan to get the product with a minimum of 13-day lead time. So timing here is very important. Next, I'm going to hand it off to Liam.
Thank you, Maggie. As mentioned, the model may cause changes that involve risks for both Caterpillar and its dealers. For example, a disruption in service may come as a result of a change in the parts delivery. In order to mitigate this risk, Caterpillar should increase the level of safety stock at its central distribution center in Latin America, store number 55. This would decrease the lead time to other dealers in Latin America. In addition, Caterpillar should work with its dealers to increase the length of their forecasts and decrease the risk of emergency stockouts. In the long term, Caterpillar should work more directly with their dealers to develop better forecasting techniques and tools. And furthermore, Caterpillar should develop a network among their dealers so they can communicate information about stockouts and utilize extra capacity in other dealerships. In order for the model to be successful, Caterpillar needs to communicate the need and appropriateness of the model with all of its dealers. We recommend that Caterpillar does this through one big collective mandatory steps for them to implement it in their dealers. In addition, we also think that Caterpillar should offer opportunities for the dealers to give feedback so that Caterpillar can continually improve on the model over time. We hope that you find our model and recommendations very helpful